This is a tower defense game with hundreds of thousands of units that I first started developing a few months ago. Pretty cool, right? The unit count is fluctuating at around 200,000, and yet our game still runs at a stable 40 to 50 FPS. But I'm thinking we can do better. You see, all of the computations in this game are done on the CPU. Aside from some rendering optimizations involving instancing, all the logic of the game is controlled by the CPU. In this video, I'll be learning to write compute shaders in order to harness the power of the GPU to simulate even more units. Before we begin, I'd like to get a few important things out of the way. First off, it's best to view some parts of this video in full screen because there are often so many units on screen that the video might look kind of weird from farther away. And another thing, I've actually made the code for this project public on GitHub, so if you're interested in how I got this all to work under the hood, the link to my code will be down in the description. Also, it's important to note that I've largely been able to not care about graphics in this little demo that I've made because each unit is literally represented by a single pixel. However, I still do think it's very impressive to be able to simulate 1 million units in real time, regardless of how abstract they might be. Okay, without any further ado, let's begin. As per usual, I'm going to be using the Bevy game engine and the Rust programming language to create this project because I've become quite familiar and fond of the minimalistic architecture and functionality within that engine. Luckily for us, getting started with compute shaders in Bevy should be relatively painless because Bevy already has a compute shader example where the shader modifies the pixels of an image on the GPU to simulate Conway's game of life. Conway's game of life is a type of cellular automata where every pixel in an image is updated based on a certain set of rules, resulting in this lifelike sort of behavior, which is perfect for us to simulate in parallel on the GPU with compute shaders. You might have just heard me mention the simulation running in parallel, and you might be wondering, does this have anything to do with multi-threading and parallel computing? Well, yes, this is actually a large part of what makes the GPU so quick. The GPU can be thought of as a parallel computing machine, which is very clearly seen in the case of fragment shader programming. For those who don't know, fragment shaders handle the actual drawing of pixels onto either a texture or directly to your screen in the graphics programming world. You can imagine that the computations in fragment shaders are often complicated and also need to be repeated millions of times. This process must be quick because these computations are vital to what you see on screen each frame. What makes this process not take an abnormally long amount of time is largely due to the fact that computations are done in parallel, which means that computations are done at the same time to rapidly speed up what would have taken a single worker thread an extremely long amount of time. One of the downsides of fragment shaders for our current goal of creating a battle simulator is that they cannot retain data between frames, and it is also hard to access data between threads. Originally, I was going to include a section here where I showed the limitations of fragment shaders through an actual implementation, but I deleted it from the final draft of this video because I thought it was a bit too off topic. Anyway, let's get into the ways compute shaders retain data. The first way compute shaders can do this is through textures. What I mean by this is that both fragment shaders and compute shaders can store data within the color of each pixel. This is mostly helpful in creating cellular automata like Conway's game of life, or creating pixel-based fluid simulations, otherwise known as Eulerian fluid simulations. The second way compute shaders can retain information between frames and threads is through storage buffers, which are most commonly arrays that the compute shader can read or write to. Okay, so what are the proper steps to creating a GPU accelerated particle simulation with compute shaders? We first update the buffer through a pass in the compute shader, which we will call the update pass. The particles are all updated in parallel, and these computations only need to be done once instead of multiple times for each pixel. But just calculating the position of the particles isn't enough. After all, we haven't really rendered the particles yet. And a way we can do this is through another compute shader pass which iterates through our storage buffer and directly places pixels onto our texture through a function called texture store. There is probably a different name for texture store in other shader languages, but in WGSL, which is the shader language that I'm using, this is what the function for changing the color of a pixel in a texture is called. This approach is much faster, much easier, and would definitely outperform any type of CPU particle simulation if done correctly. So let's get to work doing just that. Okay, this doesn't look too impressive, but I've done exactly what I said I'd do. This is indeed a working GPU accelerated particle simulation. I've just given each of the particles the extremely simple behavior of moving to the right. This doesn't make for much interesting behavior, but it definitely shows that our particle system works for the most basic of test cases. In other words, all we have to do now is adjust the behavior of this compute shader to suit our needs. But this is easier said than done. After all, our final goal in this video is creating a battle simulator which is able to handle millions of units. If we can stably simulate 200,000 units on the CPU with minimal lag, then it's not far-fetched to try to reach for the millions on a GPU. Given the simplicity of the situation right now, it's probably a good opportunity to explain how computers are written. Let's start by taking a look at how they're dispatched from the CPU. We can think of compute shaders as a 3D block of computation groups, or work groups as they're actually called. Work groups themselves contain a number of worker threads inside of them that are also declared as a 3D block. This dispatch operation specifies exactly how many work groups are contained within the block through the edge lengths of such a block. However, there really isn't a rhyme or pattern for setting the dimensions of the block. For iterating a 1D array like we're attempting to do right now, we only really need to be using one dimension. It might be different if we were trying to iterate a texture, and since textures are 2D, we might be using the X and Y dimensions to specify a 2D pile of workgroups instead for convenience. But since it's convenient for us to iterate an array, we can just dispatch a very long line of blocks like I'm doing right now. We want one thread to be updating each unit per frame, and since there are 16 threads per workgroup, we can just divide the total amount of units by the size of each workgroup to get the total amount of workgroups we need to iterate through the entire buffer of units. Now let's look inside the actual shader. The workgroup size specifies the dimensions of the thread groups inside of the block. You can think of this as cutting each individual workgroup block into thread units that will do the actual computations. The threads will then execute in parallel this function which is below the workgroup declaration. Now what exactly is a global invocation ID? Well, for us, this represents the index of the unit in the array which we are updating, but in actuality it is the global unique ID of the current thread. In our case, since we created a block which has the dimensions of 1 in all but the x direction, the x value of this invocation ID will actually correspond to an index in the array. This concept requires a bit of spatial thinking, so I recommend you practice on your own a bit if this is confusing to you. I'll also link a particularly helpful article in the description in case you do better with written documentation than with explanations like this one that may or may not be too clear coming from me. So before we go ahead and implement a full-on battle simulator, let's first try something a bit simpler. Let's start by implementing Boids, which is a flocking algorithm developed by Craig Reynolds in 1986. But since 1986, it's become very famous in the programming community as a simple set of 3 rules to create flocking agents. It has also become a way for graphics programmers and game developers to test and benchmark how performant a language or framework is by writing a Boids program inside of whatever they're trying to test. We'll start off by making all the Boids move towards the center of the screen because we need to give the Boids something to do in order to see some sort of behavior. The first rule of Boids is separation, which basically just ensures that the Boids don't merge into each other. This is done by modifying the velocity of a Boid so that it steers away from any other Boids that get within its protected range. You can think of this as the most simple form of collision resolution. Coincidentally, this is the only portion of the Boids code that we're going to keep for our battle simulation because we don't want our units to merge into one another while fighting the enemy. Some battle simulations just make their pathfinding better, so they don't need to worry about collisions between units at all, but I think it makes the fight look a lot more dynamic with collisions even if the performance suffers a lot from attempting to resolve collisions. The second rule of Boids is alignment, which basically makes it so that nearby Boids face in somewhat the same direction. This code just makes the velocity of Boids more similar to each other if they are close enough to be within a visible range. Just a note that these last 2 rules won't actually make it into the final product because I feel like they'll be sacrificing too much performance to really benefit us too much. The final rule of Boids is cohesion, which makes it so that our Boids stick close together to nearby Boids to sort of make them feel more like a group. This is the opposite of separation. The code, however, is a bit different. Each Boid slowly converges towards the center of mass of nearby Boids. It's important to understand the difference between negative avoidance and cohesion. If they were the same thing, what would even be the point of running a cohesion function? We can just decrease the avoidance factor and tell everybody we've implemented the cohesion rule. With those rules all implemented, we finally finished with our Boids simulation. With around 100,000 units, we're running at around 40 FPS, which isn't bad, but it also isn't the best. At this point, it should be noted that the simulation is currently checking every Boid with every other Boid on the screen each update, and this means that it is actually doing things in a very inefficient manner. For those who know, the algorithm is currently running in O(n)², or exponential time complexity. To speed up our computation, we need to get rid of the useless checks between units that are very far away from each other, so that we don't need to iterate through as many units and perform computations between them. So in simple terms, we need a tool to make Boids aware of which units are actually close to them. This tool is called a spatial hash, and the spatial hash which we implement is going to be the most simple kind, which just divides the world into a grid and places the Boids within them so that Boids only need to perform computations with the grids that surround its current grid. Now this would be a relatively trivial task on the CPU. First, we would create an array of grids. Each grid would contain a dynamic array of Boids. Every frame, we would place Boids into these arrays depending on where they are within the world. Then, there's just the trivial task of iterating through all the grids and updating the Boids within them accordingly. It should also be noted that a Boid can't only check with Boids that are within its own cell, but it also needs to check with Boids that are in its neighboring 8 cells. This is because if a Boid is on the boundary of a cell, it can miss collisions with another Boid that is on the boundary of a neighboring cell. This concludes a possible approach to spatial hashing on the CPU, but this is neither the most efficient approach or even a possible approach on the GPU with compute shaders. One major issue is that recreating a 2D storage buffer every frame is extremely expensive. Another limitation is that we would need to have vectors or arrays of dynamic lengths, which to my knowledge is not possible within a compute shader. So how do we go about creating a spatial hashing algorithm on the GPU with compute shaders? Well, we would have to begin with the sorting algorithm. I know some of you might be very confused right now. Why do we need a sorting algorithm? But stay with me. Let's say we have a world of grids with each grid being assigned an ID based on its position in the world. Now let's add some units into this world. We can first calculate which grid each unit is contained within and assign the unit that grid's ID. If we then sort our storage buffer array of units with the grid IDs in mind, then the units within the same grid should be next to each other in this array, right? All we have to do then is to create another storage buffer array of indices with the size of the amount of grids in our world. Inside this array of indices, each index would correspond to a grid ID, and the data contained within the array is the starting index or boundary of each grid within the array of units. All we need to do now to iterate through the units in a grid is first find the grid ID of that grid and feed it in as an index to the array of indices. This will give us the left boundary of where all the units in a grid are positioned within the main array of units which has been sorted at this point. Now we just need to move forward from this index while updating and applying logic to each unit along the way until we reach the end of the array, or until we've reached a unit with a grid ID that is different from the one that we are querying from, which will indicate that we no longer need to iterate because we have gone through all of the units in the grid which we are querying from. It should be noted that this version of the algorithm hinges on the fact that our world is not infinite, because otherwise we would need to come up with another way to generate unique grid IDs and make a different kind of indices array, because the size of our indices array is currently the size of the world, which is quite a nice optimization. And an infinite world would mean that this array would have an infinite size, which is not really manageable in any context. For those of you curious where I got the idea to use a sorting algorithm, I'm not really that smart, I can just Google things. Specifically, I was able to develop this deviation of algorithm from watching a Sebastian Lag video on fluid simulations. This type of fluid simulation that he was making in the video was Lagrangian. What does Lagrangian mean? Well, go read the Wikipedia article. But in the context of a fluid simulation, Lagrangian means that it is particle-based. In any performant particle simulation, there needs to be some sort of spatial hashing present. That being the case, Sebastian created a very clear visual presentation on a spatial hashing algorithm which I encourage you to look at for yourself, and which I will definitely link in the description. Anyway, we need to actually implement a sorting algorithm now. This might seem easy at first. After all, sorting algorithms are often taught to programming beginners as a way to hone their skills, and there are a lot of easy to understand sorting algorithms out there. It is unfortunate that the one which we are going to be implementing is one of the more obscure and I dare say weird sorting algorithms. Bitonic Merge Sort is a parallel algorithm for sorting. It is also used as a construction method for building a sorting network. Did you see the key word in this sentence? Yes, the reason we will be researching this very obscure algorithm which you've probably never heard of is because of the fact that it can run in parallel. I'm probably sounding like a broken record at this point, But computers and the GPU love parallel computing, so this should be the right algorithm for us. How do we actually implement this algorithm? Well, past me also wanted to know the answer to this problem, and after going through a number of resources, I found that the best way for me to understand this algorithm was through a YouTube video by Null Pointer Exception. If you find my explanation later on in this video to be inadequate, I would highly suggest watching his video on the topic. It's a lot longer than my explanation, and he's probably a lot more experienced than I am with algorithms like this. It should be noted that most example implementations of Bitonic Sort use recursion. However, on the GPU, we don't have the luxury of recursion, so we are actually going to need to write an iterative solution for Bitonic Sort with for loops and the like. This is actually a lot harder than I first anticipated, but luckily for you, I will be breaking down my iterative solution to this algorithm step by step. Let's start with a visual representation of Bitonic Merge Sort. But first, what does the Bitonic part of the algorithm mean? Bitonic refers to the algorithm's manipulation of Bitonic sequences, which is a list of numbers that are first monotonically increasing and then monotonically decreasing. Make sure you understand that concept because it's going to be very important moving forward. After all, the foundation for Bitonic Sort is an understanding of Bitonic sequences. To be clear though, the Bitonic sequences that we deal with in Bitonic Sort are all split down to half, which means that they are increasing in the first half of the array and then decreasing in the second half of the array. Let's say we have a Bitonic sequence. The green shaded parts represent increasing portions of the array, and the red shaded parts represent decreasing portions. The sequence is first increasing and then decreasing, but what if we just cut off the second half of the sequence? Take a look at the result. Isn't this just a sorted array? Well, now the question is how we can go from a Bitonic sequence to a sorted array without having to cut off half of the array. Well, the opposite of separation is combination, so we need to find a way to merge smaller but more numerous Bitonic sequences into larger Bitonic sequences that are less numerous. Our array basically starts out as a very large number of 2-number Bitonic sequences. If we can then turn these 2-number Bitonic sequences into 4-number Bitonic sequences, these 4-number Bitonic sequences into 8-number Bitonic sequences, and keep going, we will reach a point where our entire array has become the first half of a Bitonic sequence, which if you'll recall is supposedly monotonically increasing, and at that point our array will have been sorted. But in order to turn these smaller sequences into larger sequences, we need to find a way to merge Bitonic sequences. Basically, each pass in this list of steps that I've drawn out calls Bitonic merge once for an array with Bitonic sequences of increasing size. A side effect of this process is that our array needs to have a prerequisite size which is a power of 2, or else our algorithm cannot operate correctly. There are ways to bypass this restriction, such as padding in numbers of infinity, which will inevitably be moved to the end of the array. But I didn't really feel like doing all of that sketchy stuff, so in this game, our array size is just going to be a power of 2. Okay, I went a bit off track, but let's get back into the Bitonic merge operation. So this diagram which I've drawn shows the merge operation happening several times, but it probably still seems like black magic right now. After all, the sequences are just automatically merging here without any detail actually being shown. So let me show you a real example of the merge operation occurring. Given this array which has already been made into 2 Bitonic sequences each of length 8, let's convert it into 1 Bitonic sequence of length 16. Once we've finished a Bitonic merge operation, our new merged together sequence would contain a different pattern of increasing and decreasing, because the new sequence is twice as long as the current sequence. So instead of switching between increasing and decreasing every 4 elements, the sequence would switch between increasing and decreasing every 8 elements. So I'll switch up the green and red shading of the array for now. The way we actually merge smaller Bitonic sequences into a larger Bitonic sequence is through a series of compare and swap operations. We first compare the two halves of the Bitonic sequence and check every element in the first half with its corresponding element in the second half of the sequence. This half of the array which we are merging should be made to be increasing as indicated by the green shading, which I've created to help visualize Bitonic sort. So we make sure that the number in the second half of the array is larger than the number in the first half of the array. If the part of the array which we were comparing had been part of the decreasing portion of the array, as indicated by red shading, we would have to make sure that the second element was smaller than the first element instead of vice versa. Anyway, after this series of comparisons, you might notice that the sequence still has not been completely merged. After all, the first half of the array is clearly not monotonically increasing right now. We haven't done anything wrong, we just need to perform multiple compare passes. this time with sequences of an even smaller size. Specifically, we perform comparison operations on sequences that are 2 times smaller, and we continue this pattern of performing comparisons until the sequences hit a size of 2, at which point there is no need to keep comparing them because we have successfully completed the merge operation. You might notice that each comparison pass actually has the same amount of comparisons. This number of comparisons is actually the total size of the array divided by 2, which is really convenient for us because we can now use this number to parallelize the comparison operations in this algorithm by assigning a thread to each comparison. For more specifics on my implementation of this sorting algorithm as a compute shader, feel free to check out the GitHub repository, which I will be linking in the description. I hope I've done a good job explaining the algorithm in this portion of the video though. Now that we've finished with the sorting algorithm, we can actually write the code to implement spatial hashing. If you remember, I actually went over how exactly this was done in an abstract manner earlier in the video. Looking back at that portion of the video might be helpful in understanding the code implementation that I'm about to show. The first step to this implementation is actually assigning a hash ID to each unit in our storage buffer array. We can do this again in parallel with the compute shader pass. The code is relatively simple, and we can actually write a helper function to make the function seem more clean inside of the compute shader. After this pass is finished, we can then move on to sort the array, after which we can begin creating our indices array from the sorted array, which is quite simple and just requires a pass through all of the units in the array. Okay, now let's get into how we actually use all of this information which we've just created. Let's start off by just iterating through the current grid that our unit is in. You might immediately notice a lot of clumping on the boundaries of each grid. This is because we're ignoring my warning earlier, where I said we would need to also check the neighboring grids of a cell so that the units which are in another grid but are still close to the unit are also considered in physics computations. So I've created this constant array of 2D offsets which define which grids next to the current grid will be iterated through. All that's left to do now is iterate through this array, find the hash ID associated with each neighboring grid, access the starting index by querying for it within our indices array, and finally iterating through our main array from the starting index to the end of the array, and breaking when we encounter a unit that is not within the grid which we are currently iterating. A reminder that this is all possible simply because we wrote a sorting algorithm to sort an array. If we run the code now, you'll probably notice that the game is running a lot more smoothly with the same amount of units. At this point though, you might be stumped, because at the start of the video I clearly showed a 1 million unit simulation being run at a stable 50 to 60 FPS, and the FPS which the game is running at right now does not even come close to that speed. Don't worry though, there is a final optimization which is actually really impactful on FPS which I will be implementing, and that optimization is what I would like to call frame procrastination. Okay, in reality though, I just plan to run our simulation on a fixed update with a relatively slow time step, so let's do exactly that. Since being inside of the render world in Bevy complicates things a lot, I actually needed to implement my own fixed update system instead of relying on Bevy's built-in fixed update system. Okay, now this is very impressive, 100 FPS with 1 million units being simulated. There is however a slight problem. Why are the units moving in such a clunky manner? Well, this is a side effect of frame procrastination and running away from your problems. The fact of the matter is we're actually running this simulation at an interval that is not in sync with our frame rate and is actually a lot slower than our frame rate. So our simulation is effectively not running at 100 FPS, and in this case we're sort of lying to the player. To fix this though, we can lie even harder to the player. Fake it until you make it is a valid strategy here. To fake the fact that our simulation is running at a lower time step than our refresh rate, we need to create an interpolation system where our units smoothly move between their actual physics updates even when no actual physics calculations are being done. Luckily, I have experience with this particular type of interpolation because I've actually done it to create more accurate platformer movement in some of my other games. I'm not going to go into too much detail, in part because my implementation of the fixed update loop in Bevy's render world is conventionally questionable. Reading this article on fixing your time step can help you implement a similar type of interpolation if you want to do so in one of your projects. Specifically, the last part of the article shows you how to use your accumulator value in a fixed update to calculate an alpha. In the end though, my implementation did work, and even though you might notice that our frame rate is no longer a satisfying 100 FPS, it sure is a lot faster than it would be if we didn't create this very strange time step system. Anyway, since all of our major optimizations are out of the way, we can get started actually creating our battle simulator logic. First, we have to create a way to identify which side of the fight our units are on. What I did was assign each unit an ID by incrementing by 1 each time I spawned them in the initial buffer. Then, if the ID was in the first half of the array, I discerned that they were on a different side than the units that had IDs in the second half of the array. It is important to note that we aren't able to use indexes to determine the side that a unit is on because we had to sort the array for our spatial hashing algorithm. Also, there is the easier solution of just assigning each unit which is on a team a a variable containing an integer of value 1, and each unit that is on team 2, a variable containing an integer of value 2. However, using a unique ID like I'm doing right now is actually advantageous because it gives us an easy way to identify units based on an ID if we ever need to access this type of information in the future. Checking if a number is smaller than something isn't really too expensive of a computation, especially if it's done on the GPU, so that is why I decided to create the system the way it is right now. With that done, our units are now moving towards each other. I also did engineer a system where the units start moving to the origin point once they get close enough to the y-axis. In case units eventually slip by once there are only a few units left and just infinitely move in one direction without finding enemies, this is what I implemented. All that's left to do now is to get our units to detect an enemy close by and have the two units start moving towards each other to initiate a fight. When a unit dies, I change its hash ID to -1 so that it will be sorted at the start of the array and also not be included in the indices array, which we use to look up the start index in the main array for each grid. This means that no excess calculations will be done for units that are already dead. Additionally, I had our rendering system check to see if any of the units have a hash ID of -1, and if they did, they wouldn't be rendered. Effectively, with these changes, we have removed the dead units from the simulation. Next, I added some health to our units so that they don't die instantly upon meeting each other, and our game was complete. I also think that it's nice that I don't need to add a delay timer for the units to attack each other because our simulation timestep is already so slow under the hood that the attacks seem to have a delay anyway if they were being run in the fixed update. It would be nice if we could get rid of the units from the main array to speed up our sorting algorithm, but I don't want to deal with losing data by removing units, and modifying the size of a storage buffer felt like it would be very painful on the GPU. It was a happy little incident, but I'm very glad that this project worked out the way it did. I think that it is quite an accomplishment for a computator newbie like me who just picked up the system to be able to simulate 1 million units on a comfortable frame rate of 60 FPS. Anyway, I hope you guys found this video to be helpful or interesting in some way. I know that this video was a lot longer than my usual videos, which is just me experimenting with a new type of video format. I do go into more depth with some topics, but I do know that this format isn't as concise or easily consumable for some people. If you made it this far into the video, make sure to drop a like on this video and consider subscribing to the channel. It would really motivate me to post more content, and I would really appreciate the support. Let me know if you would like to see more of this type of content instead of my regular content, or if I should just continue making my regular form of content. Goodbye, and I'll see you guys in the next video.